Hello and welcome to lesson 7.6, some applications of the dot and cross products. We're going to revisit some applications of the dot product, but we're also going to look at some applications of the cross product today. One application can be found using the measure of torque. Torque is the measure of a force acting on an object that causes it to rotate, and is given by either the cross product formula, the magnitude of the cross product, in either form. Here I show a wrench that is going to be a distance right here, distance from this point of rotation, which is given by the magnitude of r, and we also have a force being acted upon it right here in newtons. So this distance is usually in meters. This measure is newtons. So these values actually don't turn out to be joules like we saw before. These actually turn out to be what are called Newton meters. You're multiplying these two units. Now the angle that you have right here, theta, is actually the same angle between the two vectors. So you can replace the vector f going this direction, and your angle theta is still in between. Okay, so let's try this. A force of 60 newtons is applied in a clockwise direction at 80 degrees to the handle, 20 centimeters from the point of rotation. So let's draw a little example of what we have here. So this is our point of rotation pointing outwards. This is 20 centimeters. Clockwise direction means it's coming down this direction. And this is 60 newtons at an angle of 80 degrees. So this angle is 80 degrees. Meaning if we move the 60 Newton force here, this is also 80 degrees. Now realize it's rotating from this point to this point. Okay, so the magnitude of the torque can be calculated by taking the magnitude of r times the magnitude of the force times sine of theta. Well, r is 20 centimeters, so in meters that's 0.2. Force is 60 newtons, and angle is 80 degrees. So using my calculator, the magnitude of the torque just turns out to be about 11.8 Newton meters. So using my right-handed rule, we can determine which direction does the torque vector point. So remember, use the right-handed rule. We're going to put our fingers along the vector that's our rotational force, so r. And you're crossing to the vector f. So going towards the vector f, so curl your fingers towards f. The only way your finger can point is your right-handed points inwards. So if you ever wanted to describe this, you can write this as into the page. and therefore it's kind of like screwing it in. Okay, let's take a look at another example. So, a force with units in newtons is defined as F as 200, 500, and 600. Acts on an object, moves it from negative 403 to the point 254, which is measured in meters. Interesting. Determine the work done. So we start at this point, negative 403, and we go over to this point, wherever it might be in three-dimensional space, 2, 5, and 4. So this is our distance traveled. Let's say our vector points, our force vector points in this direction, which was 200, 500, and 600. So, to remember, to calculate work, that was just the dot, oops, my apologies, it wasn't a vector. To calculate work, we're just taking force dotted with distance. Well, the distance vector, I'm going to have to work out first. That's just going from negative 403 to 254, or 254 minus negative 4, 0, and 3. So my distance vector actually turns out to be 6, 5, and 1. So now I can work out my work. So now I'm taking vector 6, 5, 1, and I'm dotting with 200, 500, and 600. So that's equal to 1200 plus 2500 plus 600, which gives me a grand total of 4,300. So therefore, total work done is 4,300 joules. Okay, let's see some other properties. Some calculations will require us to calculate what is called the triple scalar product. So, triple scalar product can be given by U dot V cross W. Please realize that V cross W has to be worked out first in order to dot it with vector U. Another option is you can actually work out U cross V and dot W. It gives you pretty much the same kind of result, it just might be a plus or a minus off from that. Other calculations require the triple vector product, which is just U cross V cross W. And again, you can cross any of the two first, and then work out the second one next, and it just might be a multiple plus or minus of that value. Now, a parallelepiped, which is kind of like a cube that's been transposed into making a parallelogram on all sides. Let's say we have a parallelepiped that can be described using vectors U, V, and W coming out from one corner. So let's say this is U, this is V, and the other one is W. Well, in order to find the volume of such an object, you just have to work out the triple scalar product's magnitude. If you just wanted to find the volume of a tetrahedron, which is partly this piece right here. The volume of a tetrahedron just turns out to be 1/6 that triple scalar product magnitude. Okay, so let's apply this to a given set of values. So we're going to work out the volume of this parallelepiped, seeing that it all extends from the point O. So OA, OB, and OC. So to find the volume of this, we need the magnitude of OA dotted with OB crossed with OC. Again, you can do in any order that you prefer, if you like. Doesn't really matter. It'll work out to be the same thing. So I'd encourage you guys to now pause this and work this out for yourself and verify your answer after you're done. Okay, so now that you've done that, I'm going to work out the cross product here, of course, first. So my first one is the value of 4 minus -6. Next one is 21 minus 12. Next value is 12 minus -14. Okay, this turns out to be 10 minus 36 plus 130. Because I got the absolute value signs on here, or the magnitude signs, this just tells me it's 104 units cubed. And there's my volume. And thus concludes this lesson.